Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Joe Hellerstein from Berkeley. Joe is a database guy who has seen the light and decided to go and apply databases to sort of everything. I believe his first stop on the excursion was sensor networks, and has now moved on to parallel distributed computing. And I saw this work a little while ago and thought that this was a very new, cool idea for how to program very large-scale systems. And fortunately, Joe and a bunch of his students are up here today to talk about it. Most of you have probably seen the meeting after this. They're also around this afternoon, so if people want to talk to them, there'll be some time after 2 p.m. where you can get together with them. And just probably the easiest thing to do is to just send me mail if you want to get together with them, and we'll work something out. So it's a pleasure to introduce Joe, and welcome.
Thanks. Yeah, so why don't I just jump right in, give you guys a sense of what we've been thinking about over the last couple of years. And because the intention today was to bring up the gang and brainstorm, there's a lot of, well, there's not a lot, but at least there's some at the end, stuff we don't know yet, haven't figured out, thinking about. So conversation starters stuff. So this is joint work with a whole team of folks, including including a collaboration with folks at Yahoo, and Rusty Sears moved from the top list to the bottom list in the last year. So that's been a good collaboration for us and a lot of fun. So what I'll try to talk about today is kind of what our take on what cloud programming is about. We can, if the audience thinks it's worthwhile, do a little quick tutorial on Datalog, because that is the foundation for what we're doing. My assumption is we want to do that, but stop me maybe, Jim, if you think that I'm...
No, why don't you do it?
Well, I'll do it. OK, yeah. And that's going to cut into our time to talk about the real stuff, but it's probably worth it. And then our project Boom, I'll give you a look at what we've done to kind of prep for it in a way. It's sort of, we did an excursion or an experiment over the last year in that realm. And then a flavor of where we think we're going to go with the language for Boom, which is Bloom, and then some research directions. So I shouldn't have to talk too much about cloud at Microsoft, but our take on it is that we're interested in it as a programming platform. All right, and it's an unusual programming platform. Every new platform brings different features and challenges. We know many of the features we're seeing in the cloud: a shared environment, dynamic sets of machines doing computations that evolve over time for services. And a lot of the applications people are talking about are very data intensive, and some of them also session centric, involving users on clients. And of course, for a platform to really be interesting, it needs programmers, right? And when you look at something like a new platform like the iPhone, what's fun is that there are all these people thinking up crazy things to do with the iPhone that people at Apple probably never thought of. And so when you think about the cloud, you ask yourself, well, if there's going to be an app for that in the cloud, what are they, and who's going to build them? Right? I mean, we can name some of them now, but it's not a long list. So how are we going to get the people who aren't in this room to innovate in this space, right? And this leads to the doom and gloom, which is in the title of the talk. Cloud programming is really hard because it's parallel and it's distributed. And there was a blog post by Dave Patterson where he quoted John Hennessy, and the two of them have this very dark view of the future of computing that they were using to raise money from the federal government. So there's two ways to make someone interested in what you're doing. You can say, my stuff is really great, or that you can say, you're really screwed if you don't fund me. And they went for option 2. But Hennessy had this quote, when we start talking about parallelism and ease of use of truly parallel computers, we're talking about a problem that's as hard as any as computer science has faced. I would be panicked if I were in industry. Fortunately, I'm running a large university with a big deficit, so my life is easy. But really, it's a challenge in this space, because I think when the programming model is so hard, it stymies innovation. So programmers programming in the cloud today are either expected to knock up single node software and just replicate it. And that's fine, but that's not innovative use. That's like running, that's like running a telephone app on your iPhone. It's like, well, yeah, sure, but that's not going to sell lots of new iPhones. But if you want to write something new, you have to orchestrate concurrent communication and computation, tolerate delay and failure in this elastic, minimally managed environment. And there's just very few people who can be expected to program like that in the traditional languages like C# and Java and so on. So this is a roadblock for the folks we really want, or the creative people who think about stuff that's about what the users want. It's not about computers, right? So the kind of creative software developers who aren't necessarily great developers, but they have great ideas. And think about all those iPhone apps, right? Those are not necessarily PhDs in computer science writing those things, but it's what makes it interesting. And frankly, you know what? Building stuff in the cloud is hard for you guys too, right? Even if you have a PhD in computer science or you're the world's best programmer, this is a lot harder than writing single-threaded code. All right? And so our take on this is basically to look at inverting kind of the control structure or the way we think about programs, where instead of the kind of von Neumann model where there's a processor manipulating memory, let's turn it upside down and say that computing is subservient to thinking about state. And this is where, Jim was sort of making fun of me a little bit, but I think as the database point of view may be helpful. You say, well, computation is secondary. What you should start thinking about first is the information, the state of your system. So that's state like session state, the state of the system at every node, protocol state, permission state, and then of course like the data, such as it is in there too. But everything about your computation really is about deriving, updating, and communicating state. And that's a perfectly reasonable way to think about computation. And it's a way that we're going to argue is easier to parallelize, easier to deal with stuff like concurrency, because you're actually not thinking about that as your first problem. You're thinking about that kind of in service of managing the state. So the strategy we're arguing could be a winning strategy is this data-centric design, where you take all the state of your program that you would have thought of as data structures or messages, that kind of thing, and think about it instead as real data, first-class data. All right, so everything that you're going to do in your program is going to be like data in a database because it matters. All right, so you start at all your system state as first-class data, and your basic data types are going to be collections and streams. Right? Very much like you would have if you had data you cared about. You wouldn't have one-off little things in your database that are their own data structure. Right? You try to generalize. You try to come up with thematic designs that are reusable, and you schematize things. And that's what we're going to say is the right way to think about all of these structures in your program. And then computation, again, is modeling that data carefully and then reacting to changes to it and evolving the state as you go. And part of our argument is that this is a language-independent piece of what we're doing. This is not going to be about Bloom per se. Many of these lessons, if you stepped back, you could exercise them in a disciplined way in a language like C#. So just thinking about data first it's a design pattern. All right? And then the second part of our kind of our conceit is that you can use a high-level language once you've done this, like a logic language, a declarative language, where you write things as specs. So you're basically saying specifications for correctness, specifications for handling events, safety of the system, and safety of your transitions. And that you write that in a very high-level language where you're really just specifying outcomes. You get all the traditional benefits that database people like about data independence, where because your spec doesn't include the implementation, the representation and the placement of data in the cloud is left underneath the programmer's level of thought. Okay, it's left to some kind of system optimization. And then I believe we're getting, and we're not there yet, but we're getting a lens on parallelism based on logic that is quite a bit more simple, I think is the way to say it, than thinking about threads. And I'll try to give you a whiff of that today, although I think really this is something I can only do kind of very sloppily right now. And so it takes a while for me to get a convincing argument. We're getting there, though. Anyway, the point with both of these, whether you want to take the kind of language-independent design pattern or you want to also buy into declarative programming, the idea is to take things that seem to be hard problems and turn them into dead simple problems. So we're not actually going to try to do anything fancy. We're going to try to make things that you might have thought were fancy and just point out that they're easy. All right? So concurrent programming sounds really hard, but data parallelism like MapReduce is really easy. Parallel computing people like to talk about embarrassing parallelism. So let's go find all the embarrassing parallelism we possibly can. That's kind of, at some level, part of the agenda, is to make things that you might have thought hard dead simple. And on a fancier level, I think, and this is getting to the understanding of parallelism, when should you be coordinating in your programs? And one of the lessons that's coming out from thinking about it is you should only be coordinating when you're doing something non-monotonic in your logic. And a sort of simple thing to put in your pocket to take away as a slogan is you only parallelize for counting. The only thing you should ever need to do, the only thing you don't parallelize, the only thing you coordinate for is to get a correct count. Everything else that you program should just go data parallel. All right, and so really what you want to do is look at your program and figure out, when do I need to know how many of something there is? And everything else is going to be easy.
I thought that the essence of the complexity in distributed systems was this non-monotonicity.
Yes.
So are you going to be able to hide it? How can you hide it?
No, I'm going to point it out very, very clearly. And everything else, you won't even worry about it being hard. So like I say, the whole goal is to take the easy stuff and say, all that stuff is easy. Stop thinking about it. But when you're writing concurrent Java programs, it's very hard to see what's the non-monotonicity in the interactions between 25 threads. But we're going to see it very clearly. We're going to say, here's a program where all it's doing is accumulating information, and then eventually it needs to count. Map reduce. Here's a whole bunch of map, and then there's a reduce. Right? And everything should be that easy to some degree. There's really no other reason to coordinate. So let me go on, and hopefully we can talk about this more later. So it's not like I'm making this up off the top of my head. This goes way back. There's decades of theory in logic programming and data flow. What's interesting, I think, at some level phenomenologically, is that there's a bunch of folks like me running around doing this independently. It's been kind of cropping up all over the place. So it's a sign of something happening. So a lot of people have been doing declarative and data flow languages for stuff. So obviously, query processing and data analysis goes on. In addition to SQL, we now have MapReduce. That's been very interesting to watch. And my group here in yellow, we started doing networking, both sensor networks and peer-to-peer networks. Distributed computing is what we're kind of doing now. We've done distributed statistical machine learning. At Cornell, they've been looking at multiplayer games, 3-tier services. At Carnegie Mellon, robotics. At Hopkins, natural language processing. At Stanford, compiler analysis and security. There's just a lot of smart people, and we haven't been coordinating almost at all, even still, sadly, who've just been kind of going to the same toolkit to solve programming problems in a whole bunch of domains.
Is machine learning focused on what?
Just basic, general, like Bayesian inference. Yeah. And so I wrote a blog post about this stuff about a year ago. I was invited to by the CRA. And we tried to start putting together a bibliography, at least. A limited one, and would love contributions to it if folks are interested. OK, so just that was the motivation. So we're going to go back to school for a little bit, OK? And I'll just teach you a little Datalog. OK. So I had to learn this stuff in grad school, and I hated it. And I still kind of hate it. I'll try to make it painless as best I can. So here's the basic idea. Here's the world through the eyes of a real database geek. There's data, and then there's logic, which is the stuff that you know based on the data and some rules. And that's everything. OK. Here's what logic looks like. If I know Q, then I know P. OK, so that's the way to read that. If I know Q, then I know P. That's like an implication arrow. And if you want, you can think of this as SQL views. So it's an expression with a name, P. Right, but it's not stored. It's just an expression that you can compute from the data. So it's a named query that's been stored as a query, not as the answer to the query. OK, and that's all of computing. Really, at some level, if you enrich your logic enough, it's Turing complete. All right. The only thing is, like, until recently, the only people who cared about this were Europeans. Yes?
Where's time?
Time is going to turn out to be really, really important for us. So it's interesting that you asked that, because it took us like many years to bother asking ourselves that question. So thank you for asking it. It will come up later. We can take care of enough time for our purposes in plain old Datalog, actually, although we'll put sugar on top of it. And I'll show you that in our semantic stuff. Great question. Good. So far, there's no time. And in fact, Datalog, there's no time because Datalog isn't about programming, really. And so I'm starting with this pure logic thing that doesn't think about time. It doesn't even think about state update. All there is there's data, and there's what you can know from that data. And the world is static. Right? And so that's what Datalog is kind of. It's the environment. All right, so here's the classic Datalog example you're forced to learn in Raghu Ramakrishnan's class in Wisconsin in 1992. Or in Jeff Ullman's class at Stanford. So the canonical example is you have a family tree where it's stored as pairs of parent-child tuples. And you want to compute something about who's an ancestor of whom. So over here is the family tree of IBM mainframes. This is upside down from the usual family tree. And there's a rule that says if x is a parent of y, then x is an ancestor of y. All right, so this is going to be an inductive statement of what an ancestor is. All right? Base case. If you're a parent, you're an ancestor. Inductive case, if x is a parent of y, OK, and y is recursively an ancestor of z, oops, that's my little joke. Y is an ancestor of z, then you know that x is an ancestor of z. All right? So that's the way to think about this. Another way to read this is take the parent table, join it to the ancestor table, where the second attribute of parent equals the first attribute of ancestor, and do that iteratively, or if you like, recursively, until you can't compute any more ancestors. So this is just an SQL expression. It's a recursive SQL expression that joins these two tables, second attribute equals first attribute. OK? All right. And then you can run queries over this stored relation. These two things are ORed together, right? And think of this as a stored query expression. And then you can run queries over that query expression, like you can run queries over a SQL view. So you can say, find me all the ancestors of some person S. And convention, so syntax is horrible in this stuff. Convention in Datalog is capitals are variables and lowercase things are constants. Just because. All right, so this is horrible. It's old stuff. It's no fun. Some notes. This join expression by variable repetition is called unification, in case somebody wants to use that word. Variables in capitals. This is called the head. This is called the body. The body implies the head. The body can have multiple things that you're joining together. And it's set semantics in Datalog, so there's no duplicates in any of these relations. And you don't generate duplicates. And that's how you know that this will sort of terminate. You find all the distinct ancestors that can be derived from this finite data set. Okay. So the internet changes everything, right? This is old stuff. But in fact, really, if you look at what goes on the internet, it looks a whole lot like ancestors and descendants. It's just links and paths. Right? So routers keep pairs of links. I am connected to you. And they want to find paths. Who can I get to from me? So it's exactly the same program. I've just changed the names. It's exactly the same thing. All right, so this is a path-finding Datalog query. Finds all paths from S to anybody. It's the all paths query, which you don't really want to do, but it's a good start. It's all paths. This is crazy in the internet, right? What you really want, well, before we move on, let me focus on kind of why Datalog is nice as opposed to, say, an imperative programming language. This is just an expression of the output, very much like SQL. And what's pretty is that how should you interpret this? This is just logic, OK? So this is just syntax. If you ever had to take a logic class, they'll beat you over the head with this forever. This has no meaning. It's just a bunch of characters. It means whatever you want it to mean. But let's have a convention about what it means that makes some sense. So the convention is going to be find a substitution for these variables that is consistent with this expression. All right? Find a substitution that is the smallest possible one so that it doesn't contain any extraneous stuff. All right? So that's a model for this program. It's a set of assignments of the variables such that if you deleted any of them, it would become inconsistent. All right? That's called a minimal model. So you want to find assignments of the variables that you can't take any of them away. So if you want, it's given a fixed input database of links. It's the smallest sensible output database of paths. You can make up paths that aren't supported by the links, but that wouldn't be minimal. OK? And there's this nice lemma, if you want. I don't know, maybe it was a theorem once upon a time. Datalog programs have a unique minimal model. So modulo renaming, OK? There's exactly one minimal model for this program. That's really nice. That means that I can take this syntax, and there's no ambiguity about this natural interpretation of it, which is the minimal interpretation. All right? So this is well defined in a very strong sense. And another thing that, as computer scientists, is really nice is there's a very simple recursive join strategy. Keep joining links and paths, links and paths, links and paths, sticking things in paths until you can't compute anything else. That generates the minimal model. Cool. OK, so now what do we have? We have an agreed-upon logical interpretation of the program. And we have a very natural algorithm that computes it. And it's the algorithm you'd expect to run, too. So it all feels right. All right, so that's really nice. All right, so there's no implementation implicit in the program, but the natural implementation gives you the right answer. Very cool.
Question for this program, if you ignore that path excess question mark,
yes,
it would be the empty model, right? All.
Not if you had link populated with data. But yes, I agree with you. The empty model satisfies this. So typically what you'll do, and this is more annoying acronym terminology, is you'll have some kind of stored database to start with as part of this. You would actually write it down. You would say link from Joe to Bob, link from Bob to Sally. It would be part of the program. That's called the extensional database. And you're not allowed to futz with that. Yeah.
Your implementation, is it purely SLG resolution?
We're doing bottom-up.
You're doing tabular and not depth first.
Correct. Yeah, it's bottom-up execution. It's actually data flow. It's really, really doing joins.
But it's traditional Datalog semantics.
Traditional Datalog, not Prolog.
semantics.
That's right.
Okay. And no
Bottom-up,
extra.
not top-down.
Okay.
Yeah, and it's strictly bottom-up, and using magic sets and all this stuff that makes bottom-up efficient. OK, so what did we do so far? We found all paths in the internet, which is insane. What we might want to do is form paths that are like shortest paths. That would be sane. That's, in fact, what we do on the internet. Let's write that down. First, let's change our schema slightly to have costs on our links. That's what C will be. And then we can rewrite our program to propagate the costs. OK? So if we have a link from x to y of cost C, then we're going to have a path from x to y of cost C. All right? The other thing we want to do is actually construct these paths so that we can route along them. So what we're going to do is we're going to keep next hops. If we have a link from x to y, then we have a path from x to y. And if you're sitting at x, the way to get to y is to next hop is y. Okay? The recursive rule is more interesting. Here's our costs. If you have a link from x to y of cost c and a path from y to z of cost d, let's say that we're measuring something like latency, that the cost from x to z then is c plus d. Right? If we were measuring capacity, we might have taken the min of c and d. It's sort of just an example. And then the next hop thing, let's be careful. The next hop, if we know that there's a path from y to z recursively where you should go from y to n and then onwards to z, and there's a link from x to y, then there's a path from x to z where the next place you go from x is y. And then, of course, from y, you would go to n, and recursively, you would unroll the path. OK? So that's how you propagate next hops in this thing. I'll just make one note, which is I already cheated, and I'm adding stuff to Datalog. I added plus. All right? Plus is a relation. It's a ternary relation, 2 inputs, 1 output, that's infinitely big. It's all triples x, y, z, such that x plus y equals z. And now we have infinite relations. That actually extends the expressive power of the language. All right, so just, I don't want to cheat. This is actually not simple Datalog anymore. This is Datalog with function symbols. OK.
Presumably, you don't use the extensional form of that.
No, you don't want to get the whole plus relation stored. It's a drag. Yeah. Although memory is getting cheaper.
So it's really easy to implement since it's also invertible in any direction. So some functions work, some don't.
OK, but what we really want is best paths. So let's take the same program. OK, so that's the program we have so far, which computes all paths, their costs, and their next hops. And now, for each pair, source destination, look at all the paths from that source to that destination. What's the cheapest cost among all those paths? And that's what this expression says. For a source destination pair, the cheapest cost is the minimum of all the c's that you see on this side that match. This is like a reduce, where the key is xz. Or if you like in SQL, it's a group by query where the group by columns are xz. Right? And I've just extended the language again with aggregation. Right? And that's a big deal. And that's the thing where I said, the only thing that matters is counting. Really what I mean is the only thing that matters is anything that's aggregated. OK? So that's a big change. It's in the angle brackets. And that's a syntax we made up. All right. And then finally, that just gave us the minimum cost. Now we need to find the path of minimum cost, the argmin. So we take the min cost path, we join it with the path, and we find that path from x to z whose cost is the minimum cost, and its next hop. Now we got shortest paths. All right, and 5 lines, pretty good. And you can ask.
Adding stuff to the language, right? There must be
OK, not fair, not fair. I was trying to gently introduce you to the full language. I did not, in fact, make up this language to suit this example. But that's a very fair critique of the presentation. As a teacher, I've done a bad job. Yeah, I don't recommend we keep doing this anymore. We're going to stop. Good. I'm suitably chastened. All right. So we just extended Datalog with aggregation. And the funny thing about mins, right, is you can't know what they are until you've computed the full input. Right? You can't compute the min until you know all the path costs. And that's why you need coordination. Right? Whenever you want to count, how many things do I have? You have to have all the things. And the most basic thing of that is, do I have nothing? All right? So usually people talk about this in terms of negation. Do I have nothing? And you won't know that until you've tried computing everything. All right? So counting is a generalization of negation. It's just count equals 0. Yes?
So if you run this natural recursive algorithm, it's not going to terminate. Because even if you have a single loop, it's going to go off forever, right?
No, because there's no duplicates. So this particular program will basically run these rules. And again, there's a model-theoretic semantics and then a natural implementation. And
Would it infer that I have longer and longer paths to myself or something?
if you have, this is sort of loops in the internet. It will, in fact, go around cycles. This is very good. So it's a typical internet thing. And in fact, you should annotate the program to not go around cycles. Or, and my student's been thinking about that, it's not in the room, you could actually infer from this minimum, you could propagate a constraint down to here that if you find a path with same source destination, it's bigger than something you already have, you could stop. So you can push that constraint actually into here. No. That's just a Datalog to Datalog rewrite. It's not stepping out of Datalog at all. You just put a less than thing in here that you don't add something to path if the C plus D is less than something that's already in path. Yeah, sure. We have max and min and average and all these things.
Max path length is infinity.
Right, or min path length if you have negated costs. Same story. And any algorithm then has a problem because there's no non-finite answer. Sometimes you can test for that. There's conservative tests for safety of these answers. And sometimes you can't because it's kind of a halting problem sort of thing in the limit. So running around loops forever and checking for that should make you nervous, right? Yeah, these are very natural and good questions that I'm glossing over a little bit because time's short. I do actually have slides for some of this that we can go over offline, or we can just sit down and do it on the board. OK. I want to move on a little bit to talk about building real software with this. So far, what did we have? We had a logic for pathfinding in the internet, shortest paths. That was all very cute. But there was some database in the sky that we were computing this on, which is not the way the internet works. I've read research papers where they said routing should be a service. Something like Google would do internet routing. It's crazy that internet routing is this distributed computation. But that's not the way the world works. So can we implement the things the way the world works in logic? Can we basically build protocols from this specification? And the answer is going to be yes, really, really easily, using the first thing you might think of. So all we're going to do is we're going to do what databases and MapReduce and everybody else does. We're going to say, logically, there's a database in the sky. Physically, we'll take the rows in that database, or if you like, we'll take the key value pairs, and we'll partition them by key. All right, we'll horizontally partition this table. And how will we do that? Well, we'll make the programmer do it for the moment. Okay? So we'll make them put a little @ sign next to the field that's the key, the field they want to partition on. And we'll make sure it's of type address in some network addressing scheme. So think of it as an internet IP address for now, if you like. And then we'll place data, just the way you would in a parallel database, at the node that's in the location specifier.
Key value pairs, or is it
It's relations, but a single relation is a key value pair. The relation with the primary key, concatenate the fields that aren't in the primary key, they're the value. I'm trying to be ecumenical by saying key value pairs. OK, so let's do it here. The link table. Remember, this was source destination. We'll partition it by source. So if you have a tuple that says to get from x to y, it costs you c, and there's a link there, it's stored at x. And that indeed is how network routing tables are stored. You have a routing table that tells you who your neighbors are and who you can send to. OK, and if you take the union of all those tables in the internet routers, you get the link relation. All right, and paths are going to be partitioned the same. Everybody wants to know the paths outbound from them. And here's where the fun begins. Links are partitioned by the first attribute. Paths are partitioned by the first attribute. The join, if you like, the unification is on the second attribute of link, which is not the partitioning, and the first attribute of path. And by the way, I want the output partitioned by the first attribute because it's path again. So my problem is I need to compare things. Here's an example of data, node A, node B, node C, node D on a network, a linear network. Here's the link table. It's been partitioned by the first attribute. Here, the path table, same, partitioned by the first attribute. So the A's, the B's, the C's, the D's. I need to put together this link and this path, right? And they're on different computers. Communication will have to happen to achieve this specification. OK? Well, how are we going to do it? And then the output's got to go back, right? The output's got to go back. So how are we going to do it? We're going to do it in the way that I always thought was kind of disgusting in graduate school with Datalog, which is we'll just rewrite the program. So we're going to stay in Datalog, but we're going to rewrite the Datalog to an equivalent program. And it's kind of a little bit operational, frankly, but it's still logic. So we're going to say introduce a new predicate link underscore D, which is the link table, but now partitioned by the second attribute. So it's just a copy. OK, but it's partitioned by the second attribute. So it's going to look like This tuple that we wanted to look at is now there in the link D relation. Okay, and that's the whole link D relation. And now our join is on a single node. Right? This is partitioned by Y. This is partitioned by Y. Life is good. Now we can do a local evaluation of the body of that rule. And then to propagate the head back is another communication. So this is actually the distance vector routing protocol that's used in internet routers. It does exactly this. But the way it's described is not in terms of where shall the data be. See, if you look at this program, all it says is there is data laid out the following way, and there should be data laid out this other way. It's pretty declarative. When you read about distance vector in a networking textbook, what it'll say is, first, every node sends advertisements to its neighbors about its links. And then neighbors respond to the advertisements in a certain way, and this is done iteratively, which is much more operational. All right, this really just says the data shall land in the following way.
Do you advocate doing this sort of rewrite in an automatic way? Or?
Yes. So one of the things we did in this early work on declarative networking was say, you could have rewritten this differently. You could have rewritten this so we repartitioned path instead of repartitioning link. Would have been the same program. All right? And of course, we didn't write either of those things. This is done by an optimizer. This is what we wrote. We wrote something that didn't tell you how to do it at all. All right? The optimizer was the one that rewrote it. You could rewrite it another way. And the fun thing is, I said this is distance vector used in the internet. Right? Just replaying history here. So exciting, right? If you rewrite it the other way, it's dynamic source routing, which is used in wireless networks. Cool, right? So single specification, 2 implementations, one of which is better tuned to fairly stable, fairly low variance links, one of which is better tuned to very unstable, high variance links. In the networking literature, that's not the way they think about it. They think about it as, well, there's the wired protocol, and there's the wireless protocol, and I can publish a paper with a third protocol, and if I'm real clever, I'll come up with a hybrid protocol. Right? But every protocol is a research paper and an implementation. Here what we're saying is, no, there's physical properties of the platform you're running on, and you optimize for the physical properties. And by the way, the internet is changing really fast. So if you're writing one protocol for every combination of devices on the internet, you're doing something wrong. So that was kind of part of our message at that time.
Is the optimizer smart enough to do this based on cardinality? You want to do a hybrid version?
Cardinality is a bit of it, but a lot more of it in the internet context is variance of various things, like communication costs. It's not actually raw numbers. It's the predictability of things in many cases.
So are you able to express all the corner cases that the protocols deal with, like, I don't know, count to infinity, reverse horizon?
Yeah, so that stuff actually isn't so bad. But when you talk about like the corner cases in like really looking at BGP and the way they do distance vector, I mean, like any standard, they've just added tons of stuff. Can you write all that stuff down? Yeah, but then it gets ugly because it's just ugly. The spec is ugly, right? And I can't do better than the high-level spec at some point. But the algorithmic pieces of the spec, like not counting to infinity, those parts usually come out fine. Yeah. And broad strokes, it's fine. All right, and I'll try to justify that later in the talk with having built something real. These are toys. Quite frankly, what we were doing a couple years ago was interesting toys. And we were learning, and that was the point. So we had the language I showed you is something we call Overlog. It's a variant of Datalog. All right, we added aggregation and function symbols along the way, just to as we needed them. But that's actually very standard in the Datalog literature. That's a classic thing to do. We horizontally partition the tables, which again, we're talking about data. We never talk about messages. There's no send and receive in this language. There's just data and its layout. And then we added this thing called event tables, which are tables that don't persist for very long. So the data in those tables kind of evaporates quickly. And those can do things like, what is the state of the clock? So there's a tuple that tells you the current time, and it might arrive at a given time to sort of trigger things. What's a message coming off the network? Something that happened in your Java code, maybe, that's wrapping this stuff. All right, so events can be passed in as data that's sort of transient. And then the execution model is these iterated single machine fixed points. So think about this on a single node. We take a bunch of these events that were coming out of the environment. We turn them into data. We stick them in tables. Freeze the world on our local machine, compute a data log fixed point of all the persistent state we already had and this transient state we just inserted. But in the middle, in phase 2 here, it just looks like a static database. So all those events have been turned into tuples. We have a static database, do data log. Compute the outputs. and then do something with them. So generate more events, generate upcalls to Java, generate network messages, etc. Okay, so that was what Overlog was. There are problems with this, okay? And for a long time, we didn't even have it this clean. We were really confused about when does, say, state manipulation happen? When do inserts and deletes happen? How do you do atomicity? Like all this stuff was causing us enormous headaches. And later in the talk, I'll show you how to model that. We understand this now. In this model, which is pretty good, it's sort of an event handler with a Datalog engine in the middle. Okay? The database update happens atomically here before you start again. So the Datalog program you run in the middle of the loop, at least, is well defined. It's just plain old Datalog in the middle. All right? And you go atomically from fixed point to fixed point on every given node in the system.
How would that happen? Because, like the update, imagine they take the internet example.
Yeah.
The update to some part of the internet could be happening in one part of the world, and then you are doing the fixed point here.
Good.
So how can you ensure that the fixed point happens atomically?
So to be very, very clear, this fixed point is local. So all the facts you have in your local partition are run to fixed point, which generates messages. The language I showed you in the example I showed you was conveniently looked global, right? And I said, oh, you partitioned the table, but it's really a logical global database. It took us a while to just decide that that was a lie. Okay, we don't try to propagate that lie anymore, but it's a lie. So you're absolutely right. How do people really program that stuff? They think about it. They don't lie to themselves in that fashion. And I will stop doing that from now on in the talk. All right, so that was going to be one of my conclusions from the experience of programming in Datalog, is that lie was a bad lie, and we stopped using it. Yeah?
So I'm not entirely sure how this Java program is going to run, but it seems to me that there could be races because events might come, and then you might do the fixed point, or events might not come, and you might do the fixed point. Or whether it carries state across these time steps.
Absolutely right.
You could do all kinds of things.
Race is maybe not the term I would use, but the point is exactly well taken. So, look, when we're in phase 2, I sort of conveniently said whatever I dequeued in phase 1 has been chosen. Phase 2 is all well defined, and from phase 2, phase 3 is well defined, and then crazy stuff happens, and then I dequeue it in phase 1. So yeah, races can happen before I start phase 1 again, in terms of what is enqueued.
That persists.
This program
From the
does.
left-hand side to the right-hand side?
This database is state.
So once phase 2 finishes, I can just throw away the Java program and I have to restart it from only the state of the database. Is that how we should think about it?
Maybe the Java program thing is confusing. Think of it as there's many clients off on the network sending network packets. Right? These are going to be asynchronous in some sense Java calls. So there should be no difference between saying Java and saying network. Does that help?
But all the state is in the data.
All the state is here. I mean, if you have state in the outside world, because you're a separate process, that's your business. I mean, you may. That's sort of outside the model of this language. All right? But I think the thing that is important to note is that the order of the events in this queue and the choice of what to dequeue is not modeled in any way at all. And in that sense, there's definitely races here.
Yeah, the way I think about this is that the outer phases are asynchronous, but the inner phase is synchronous. There's time applied
Yes.
to the thing. And so
Yes.
it's as subject to races as synchronously clocked flip-flops are. There aren't any races. What? There are no races.
Right. It's all things come in. You do your thing. Things come in. But the problem is the things are coming in crazy order.
Yeah.
You have no control over that. This is not bad. All right. This is kind of like event programming with a really powerful event handling language. All right. And it's really not bad. And if it weren't for the horrible syntax, actually, it might even be, kind of attractive. But it's not what we want. So I'm going to show you something better in a little bit. What's happening is you guys are jumping to conclusions that it took us a bunch of years of building software to believe. So 4 years ago, we would have said, no, come on, it's not that bad. No, but now I agree with you. But give me a minute to get there. I want to argue that this language is pretty good, and I'm going to show you some anecdotes to argue for that. All right, and with language design, you revert to anecdotes a bunch, it seems to me, not knowing anything about how you do language design, doing it as an amateur. So here's a snapshot, it's a screenshot, sorry, of a research paper in the SensorNet literature. This was, I think, the best paper in Census the year it was published. It's the Trickle protocol from Phil Levis. It's a code propagation protocol. So it's flooding. You're trying to flood code to all the nodes in your sensor network. You want to make sure every node has the latest version. So everybody's going to gossip about what version do they have and give you a better version if they have something newer. except that there's contention in the radio space. You want to back off if someone else is communicating. Right? So you don't want to be gossiping if other people want the channel. And this is the pseudocode for the program from the paper. All right, and there's an implementation in the NestC event language, which is many hundreds of lines of very opaque-looking embedded C. This is an implementation in a variant of Overlog that runs on Berkeley motes. Okay, so this is David Chu's thesis work, or a little snippet of it, really. And this is the line-for-line translation. And a lot of David's code here has comments that repeat what you see over here. So this was a standalone version of this slide, so it's redundant. Almost line for line. Okay? So the way that someone who does sensor nets thinks is actually pretty well captured by this programming model, which actually in retrospect isn't surprising because it is event programming. And if you're a network person, that's a fairly natural way to write protocols.
I'm just going to come at it from a slightly networking perspective. So it seems like how the messages should be transferred has not been explicitly specified. And yet a lot of protocols worry about things like backoff, retransmissions.
That's here. I mean, this has backoff, right? Because it's trying to avoid collisions. So all this stuff about timers and doubling your timers if something happens, that's all here.
So all that is expressible. And TCP-like logic for transfers and reliability?
Sure, yeah. I mean, TCP window setting is just a very simple stimulus response pattern, right? I wait for something, it doesn't happen, I change the timer. That stuff's not hard to say. The spec in Van Jacobson's paper is not very long.
Except there's been a lot of changes since then.
Changes are good, and that's about making the network work well. The programming model, I think, is the actual specification is still pretty simple. So, and I would love actually offline. I care less about networking protocols than I used to, but offline you can tell me how wrong I am in saying that, because I'm sure I'm missing stuff. All right, so we're trying to move up the food chain from protocols because we would run into people like you and they would tell us that we didn't know what we were talking about. So we're like, okay, fine, maybe not real network protocols. Let's do peer-to-peer protocols, okay, or sensor net protocols. So now we're doing peer-to-peer protocols. But let's pick at least an interesting one. So the next thing we did was we said, I bet we could build a real distributed hash table content-based routing protocol out of this language. And we built Chord. This is SOSP 4 years ago. And we did a high function implementation with all the stuff in the paper. So all the things they said, it's not really Chord unless you add this and you add that, because otherwise it won't perform. So we added all that stuff. And the whole thing was still pretty compact. And in fact, this is it. OK. So where's Waldo on the slide? Waldo's right there. He's in the middle of the bullseye, OK, is the point. So we took something that you would have thought was hard, and we just made it really, really easy, is the point here. So this is in the spirit of saying, Chord shouldn't be that complicated. The paper's not complicated. The routing layer of the C++ implementation from MIT is 10,000 lines of C++ for something that's well described in a 10-page research paper, and most of the paper is not presenting the protocol. It's not presenting the spec. It's talking about why it's interesting. It's presenting performance results. So, I would argue our spec, our implementation is pretty close to the spec. And when you read it, that's true. And I just want to make one other point, because it's easy to get into arguments about, well, the code's dense. I don't really think it's any easier to read than C. Look, it's one piece of paper, OK? And you can print it out, and you can sit down. And I know the syntax is weird. You can get it all in your head all at the same time. You don't have to context switch. 10,000 lines of C++ you cannot print out, go to the coffee shop, and just read and understand. It just can't be done. So we like to talk about orders of magnitude code size difference, because I think anything else is kind of irrelevant. But when you're 2 orders of magnitude smaller, now you're obviously saying things at a different level. Okay, and that's the point I'd like to carry away. Obviously, you can't read this code. Yeah. Performance, performance is fine, man. It's fine. So, in fact, there are performance graphs in the paper. Performance of a wide area distributed hash table is not a very demanding exercise. The performance actually was more or less fine. It wasn't great. We didn't try to make it great. We didn't bother optimizing it. We got the same performance characteristics that the MIT guys got. The figure of merit, actually, is churn handling. So as nodes come and go from the system, how long does it take for people to agree on the routes? And there, they would get like 99% agreement with some distribution of people leaving the network, and we'd get like 97%. And at that point, we're like, close enough. Let's move on to the next paper. Okay, so I think it really was fine, but actually I'm not on strong ground saying that, and so I didn't even put it up.
I don't see a single primary key anywhere.
Oh, they're here. They're up there. Yeah. And they're a terrible thing. Primary keys are a terrible thing because they mean update. If you have a primary key and you want to add another tuple that's for the same primary key, that's an update. And that's non-monotonic. And that's what's happening between those loops and the state. We're going to get all that right with my copious spare time when I talk about our new language, Dedalus.
So suppose adding the key were really an event and it had a time associated with it. Yeah.
Good. Yeah, you're way ahead of us. Good.
I doubt it.
No. That's exactly what we're going to do. Precisely what we're going to do. It's great.
Good idea.
It's been done before, I'm sure. OK, so I've now brought you up to the present, and we have 15 minutes left, I think. Is that right?
Well, we have a little more.
OK. I'll go fast. At some level, this is just taking that stuff and trying to make it realer in a different application domain. So the Boom project is really to try to take this idea of orders of magnitude smaller code and apply it to building orders of magnitude bigger systems, namely cloud systems. All right? So can we really write big scale systems in this kind of code style that makes things much, much simpler, qualitatively simpler? Orders of magnitude less code means qualitatively we're saying things differently. We're saying it simpler. And we're going to build on this experience, but we want to address a broader application domain, because really fighting with networking experts about TCP is, I lose. It's just maddening, right? And I don't care enough, and most people don't, actually, so it's not a very big pool to swim in. So we're trying to actually, and this we haven't gotten to yet, but we'd like to really address real developers and not ourselves. We would like to get out of the academic language design and into real language design. So that's I got these new grad students to come in a couple years ago, and Neil and Peter are sitting here. And I said, we should design the next language. This Overlog thing, nobody can program it. We're going to design a real language. And they kind of walked in and said, first of all, we just got here. We don't even believe that your previous language is any good. And second of all, even if we take it as a given that you're our advisor and we have to believe you, we wouldn't know how to start designing the next language because we haven't built anything in the previous language. So could we please go build something and see if this is going to work? Which was really good advice. It's really nice to have smart graduate students tell you to not do what you think you want to do and just do something different. So their idea was, this was with the advice of Tyson Conde, who had been collaborating with the Yahoo guys on Pig, was let's just go build something big that's cloudy in Overlog before we design the next language. In particular, let's build Hadoop. And you know what? Let's really build Hadoop. Let's not cheat. So when somebody asks us, is it fast enough, we can, we can't say. We're going to really build Hadoop. So the goals are convince ourselves that this makes some sense, inform the design of this better language, certainly for cloud. Maybe someday we'll look at this in the multi-core space. We'll see. And they're smart guys, and they need to be famous, so we better do some hard stuff along the way. So it turns out Hadoop is really easy to build. I mean, you could build it. Has anybody seen Bash Reduce? It's MapReduce implemented in Bash. I mean, a trivial implementation of MapReduce is really easy. So we wanted to do some stuff that was hard along the way. And the metrics couldn't be just lines of code anymore because people were complaining that that was a stupid metric. We really wanted to show that the code would be better. It'd be more flexible, more malleable, and it would perform. All right? So here was the game, was we would first of all rebuild Hadoop in Overlog. And then we would extend it and sort of prototype where Hadoop is going to be 5 to 10 years from now, add availability, because embarrassingly enough, both Google's MapReduce and Hadoop have a single node as the master. It's a single point of failure. All right? And it's a scalability limit because it's a single node. And when in the GFS paper, they basically say, look, if you can't fit your metadata in one computer, buy a bigger computer. Which is so ungoogly, it's scary. So we wanted to sort of say, well, they're not going to stay there forever. Let's see how we would extend those features. And then we wanted to do some nice monitoring along the way. So this took these two guys and a couple other folks about, realistically, 3 months. Plus, we wrote a new interpreter for Overlog. And we were trying to be honest. So let's call it 9 months. But it was mostly like 3 to 4 months. So it was very easy. So here's what we did. Pete and Neil rebuilt HDFS from scratch. All right? They built what they called BoomFS in Overlog. It's about this big. And then they wrapped it up in Java API so it would be API compliant with HDFS. So Yahoo's Hadoop runs on BoomFS just fine. All right? So it really is API compliant. And that was 1,400 lines of skin in Java over these 470 lines of Overlog. All right? And then the Tyson Conde, my senior student, he was interested in the interesting bits of the MapReduce scheduler, because most of MapReduce is really boring. The interesting bits are like straggler handling and the scheduler. That's where people are kind of innovating. So what he did is he did a brain transplant. He scooped out the brains of Hadoop, which was roughly about 6,000 lines of code. Everything else is plumbing, swear to God. And he replaced it with about 400 lines of Overlog. Okay. So that's the orders of magnitude thing, roughly speaking, 20,000 to 400, 6,000 to 400. This one's a little more impressive, but this one had to really, brain transplant is harder than greenfield, right?
Is the checkpoint restart capability of MapReduce in the Java or Overlog?
It's in the Overlog. Yeah. I mean, actually, I shouldn't say that. Putting things into HDFS is in Java. Only the scheduler is in Overlog. HDFS is in Overlog, though. So the decision to put something at the end of the map phase on a local disk, the decision to put something at the end of the reduce phase into HDFS, that's in Java, but that's not interesting.
Yeah, but there's the failure handling question where you lose a node and then you've got to go find a copy.
That's all here. The decisions about how to schedule stragglers when someone hasn't answered in a while, that's all here. All the interesting decision making and policy is in Overlog. So just somebody wanted performance. So here's a super high level performance graph. This is all pairs components. So over here we've got Hadoop on HDFS. Over here we've got Boom on BFS. And then we've got Hadoop running on our file system, our MapReduce running on their file system. And what you're seeing is cumulative distribution functions, percentage of mappers finishing in blue over time, percentage of reducers finishing in red over time. You can see reduces start after maps finish. They all look the same. All right? That's the high-level takeaway here. This is running a particular boring, word count, I think, example from the paper, the usual crap. It's the same, all right? And the reason it's the same is because it's not hard. This stuff is not hard. It's all spec. There's no efficiency issues.
Slower.
Less, I think, but something like that. Yeah. I think we may have tuned that. I shouldn't claim. It's about the same. We were much more CPU intensive. I will say that. We measured that, and we were pretty open about that. All right, but the fun stuff is now. So suppose we want availability. HDFS is a single point of failure. If you go look at their issue trackers, there's like, we have a single point of failure. That's bad. Maybe we should do, what's best practices, first of all, in the issue tracker? Best practices, put your metadata on NFS. That's like Hadoop community best practices for ensuring the metadata of your, terabytes of file. And we had lots of stories from friends of, actually we did lose terabytes of stuff because we lost our metadata. It's embarrassing. I mean, Hadoop is a very immature piece of software. Much as it's a really exciting and enabling piece of software for a big community, it's pretty immature. So there is a issue tracker proposal for warm standby. You trickle logs to somewhere else, and you can at least recover as of some time in the past. We wanted to do hot standby. All right, process pairs with Paxos consensus. Because these guys wanted to do feats of daring do. Right? Well, we were trying to do warm standby. And also, we'd always wanted to do Paxos. Some folks at Harvard did Paxos in the previous system back when we were doing Cord. They did a toy version. It only would pass one decree. But it was like, wow, you can do Paxos? OK, let's really do Paxos. So Pete did the Paxos implementation. At the end of the day, it was about 50 rules, which is about as complicated as Cord. OK, Paxos is pretty complicated. That makes sense. We're talking real multi-Paxos, so it can issue many decrees. It does leader election. It's a real service. All right? And again, so I showed you David Chu's slide. This is single round Paxos. This is Leslie Lamport Paxos. So it can issue one decree and then it stops. This turns out to be really pretty. So this is Lamport Prose. And this is Peter Alvaro Overlog. Right? And it maps really, really nicely because Leslie Lamport thinks in invariance. And our language is an invariant language. Unfortunately, when you start doing leader election and you start doing multiple rounds of things, most of the papers end up looking much more state machine-y because most people are not Leslie Lamport. And when Pete can tell you more about this, but when he had to turn this into real multi-Paxos, things got less pretty. Okay. But what is pretty, and Pete put this together for a workshop paper, is kind of what he found looking back at what he had written in Paxos were the design patterns inside there. So at the bottom here, here's plain old Datalog, selection, join, and recursion. Here's what Overlog adds, messaging, aggregation, state update timers. So this is the language we provide, is down here. Above that, he found he had sort of built some patterns. He did both two-phase commit and Paxos, just to kind of compare them. So patterns, multicast was a standard primitive in both of them. Counting was a standard primitive in both of them. And then choosing amongst a group of people, which is a lot like counting. Roll call, who's around? Voting, who's around and agrees. DQ and semaphores. And these little components added up in various combinations to Paxos and two-phase commit. So I think one of the contributions by writing a really clean Paxos was to look at the structure of kind of what are the primitives in a consensus protocol. And you can ask something like, well, we cut this diagram here and gave you a language down like here. But maybe if you want a domain-specific language for distributed systems, maybe the cut's here. Or maybe the cut's here. And this is a language-independent point. This is what are your libraries that you should build? Should you just ship a Paxos library and be done? So these are, this kind of gets you to what's a good DSL for distributed systems. And I thought this was one of the things you could take away from our work that wasn't sort of tied up in buying the whole farm, right? So I wanted to bring this up. There's stuff happening because of the work we're doing where I think we're adding clarity to the discussion. OK, so that was availability. So we added multi-master availability to Hadoop file system and Hadoop. The next thing we want to do is scale out. All right, scale out is great. So Google says if your master can't scale, buy a bigger box. And that's what Hadoop does, because Hadoop does whatever Google tells them to do. And our friends at Yahoo are like, this is actually a problem. We run really big Hadoop clusters at Yahoo, and we have problems with scaling our metadata. So how can we scale out the master to multiple machines? Well, really easy. So this is the design that Neil and Pete had for the metadata in HDFS. There's a file relation. There's a derived relation that's logical, which is the paths that you can derive recursively from parent-child relationships, right? Fully qualified paths are just recursion over parent-child relationships. And then there's chunks that make up the file. Partition these tables like a relational database. And then you have a scaled-out master node. Yeah, that's right. So it took 1 day to do that. And the guy who did it was actually the guy, he's like our operating systems guy. He doesn't even, at the time, I would say he did not understand Overlog. Because he kept doing weird things with it. We're like, no, man, don't do that. And it still only took him a day. All right? That's crazy that this only takes a day. If you tried to do this in the Hadoop codebase in the Java, it would be a nightmare. It would just be a nightmare. Because the assumptions about this stuff being centralized are not in one place. And the data layout is not in one place. All right? And this is just a pure win for data-centric design. If you start by saying, I have a collection of stuff, and I'm going to store that collection of stuff, then you can parcel this stuff out, right? All right, so I'm going to skip this one because time is short and I want to move on. I'm also going to skip bragging mostly, except to say that we did build something real and we got the benefits we hope to get this time still. Orders of magnitude smaller. And performance was really good enough in some measurable way, apples to apples comparison, but there's lots more we could do. The thing is, this is not an end goal. We actually don't care about bragging about this because we didn't want to build Hadoop. The world already has Hadoop, and frankly, Hadoop's kind of dorky. So what are the lessons, right? So lesson one, when I give it a Yahoo, I say, I have this whole thing about the fascinating ecosystem that's growing up around this phenomenon that is Hadoop, yeah, which I agree. I don't talk about the software artifact as much, yeah. No, Dryad. Oh, now there's a system. It's beautiful. Just,
Good start.
It's a good start. OK, so I try to partition the lessons of this. And we're working hard to make this something that you can take home in your pocket. And frankly, we still don't really have it nailed, as Jim has pointed out to us in shepherding our paper. But part of what we're doing here, like the scale out of HDFS, is really just about thinking about the state of your system as a collection data type. It could have been MapReduce. It could have been Python comprehensions. It didn't have to be logic. It could have, frankly, been a C list library with the appropriate programming discipline to not assume that it's all in one place. Okay? You could do that in any language. Right? And I think this is just good design principle for building distributed systems. Take your collections of data, make them collections, and put collection interfaces for them. Use link. Right? This is sort of just link at some level. And I love that. That's great. And I'm not going to try to explain that. And then part of it is the declarative stuff. So we did have recursion in the file system to form paths, and we got to play with stuff like when to materialize the paths and when to leave them unmaterialized as optimizations that were separate from the design. So should we actually form the paths and store them, or should we compute them on the fly? That's all underneath the covers the way it would be in a database. We did, in other parts of the system, things like dynamic programming falls out really nicely in a logic language. And anything involving graphs and transitive closures, like network paths, falls out nicely in a logic language. And then, as I said, Lamport style invariant specification is natural in a logic language because that's what you're doing. You're doing invariant specifications, what logic is. And so certain parts of distributed systems are a good fit. And actually, the tricky bits are a good fit. And then finally, and I didn't get to talk about this, we did have this sort of aspect-oriented ability to kind of go and express invariance over all the state. Like, make sure that the number of messages sent is what we would have expected from Paxos. We didn't have to look at any APIs to do that. We just expressed that as extra invariance on the data. And so you get this kind of cross-cutting ability to put in debugging specifications. And because it's Datalog, the spec of the invariant is the check. You just write down the rule. The engine enforces the rule for you or flags you when it's not true. So there's no translation of your specs for debugging into some kind of implementation. There's no tweaking of the code.
But it seems like there's another aspect of it which you haven't talked about too much, which is a major point of leverage, which is essentially the dealing with race conditions and disambiguation of race conditions by using timestamps.
Yeah.
That's a big part of it too.
So there are a lot of limitations, and that one falls in here. All right. So first of all, the syntax is hard to write. That's fine. But worse, it's hard to read. So it's not just that people don't like it. It's that I don't like reading my own code, which I don't write that much of. These guys don't like reading their own code. You know, it's very terse syntax. Right? Not a pleasant syntax. More to the point, and this is what was brought up before, this idea that there's state all over the world and that you express invariance over distributed state is a lie. Right? And so we stopped using it. These guys are better developers than I am, I think, and they just didn't use that feature of Overlog in their code. They didn't use distributed rules, in essence. They work in special cases, like totally monotonic things, like paths in the internet. Routing protocols actually are mostly monotonic, so you can get away with that kind of nonsense. They don't work for stuff like Paxos. However, if you have Paxos, you can do it on top of that, because then you have a consistent global view. Right? So it has its place, but it's a lie in general, and so we mostly didn't use it. And you don't want a language that promotes a lie, because you'll write bad code, and you won't understand why it doesn't work. Here's a really interesting one, and obviously I'm going to stop the talk now. We're not going to get much further, but this one's come up kind of recently. Neil pointed this out. Distributed invariants are a very natural thing to specify. The way that they're specified in most systems is actually through protocol, which is not declarative. So I'll give you an example. Everybody knows from reading the Google file system paper that there should be 3 replicas of every block, right? So isn't an invariant of GFS that there are 3 replicas of every block? No. Sometimes there's 2 replicas, and then you do something, right? When there's not 3 copies of a block, then a heartbeat doesn't come to the master, and the master thinks maybe there aren't 2 anymore, and it initiates some copies, and la 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 la. What is the invariant that they're going after with this? Could you even write down what their goal is with this protocol? It's something about there should most always be 1 copy of the block, I think. Or the mean time to a block getting lost is way lower than something. But it's not like they wrote that down. So even writing down these specs for what do you want out of a distributed system is not, there's no art yet for that, really. And even if you wrote them down then, we couldn't enforce them because we can't even check them. So suppose that the invariant was indeed 99%, mean time to failure is whatever for a block. Like, how do you test that? How do you translate that spec into implementation? I don't know. So we're actually interested in this, and we think we have some ideas for sort of really software synthesis, I guess, from specification. You got to start with testing and then go on to enforcement. But the goal is to really be able to do distributed invariants. Right now, we could really only do single node invariants. And I think for distributed systems design, this is just generally important and hard and not well treated. OK, as been pointed out, Jonathan pointed out, state update in Overlog is outside the logic. It's illogical. OK, and a bunch of people have been starting to pay enough attention to us that they've pointed this out in public. So they've written papers saying, hey, you know what, P2, the system you built for Overlog, like, it does some crazy things that's not what you say in your paper. Like, and what you say in your paper is crazy too, but it's just crazy in a different way. And this is all true. So this is a problem. Okay? And it bit these guys when they were coding as well. Another thing we really haven't dealt with is, so is it better than Erlang? Why? I don't know. I actually don't really have a good answer. I have ideas for answers. And that's one reason I really want to talk to you guys about Orleans, is I want to understand, maybe by hearing each other's pitches for what's good, we can get more clarity on the pieces you like. All right. So I think with my very brief remaining time.
Is good the right question or necessary the right question?
Elaborate, please.
Well, as soon as I have a monad, which is link or Haskell or link from any of the .NET languages, I can make this happen. I mean, I can embed Datalog inside of any of these and make sure that all the state is contained in the declarative part, all the rest of that. And once I have that, now you're talking about programming practices. But better, they're all equivalent, they could actually all interact with each other. So I think it's more of what's necessary. C++ doesn't give me what I need by itself to actually pull this off. Now, we can enforce it. I can give you libraries you have to live inside of and all the rest of that. But the language itself doesn't help by itself.
Yeah, I have a real hard time with that line of thought because, of course, anything Turing complete is fine. It's necessary it's like, I understand that from a complexity point of view, but everything after that is programming practice. I mean, so I think we would just agree that it's all about good. And your definition of necessary is really a strong version of good.
Sure. Okay.
Yeah. Yeah. And
you might want to say which one of these makes it more automatic to do the right thing?
Yeah, maybe. How easy is it to shoot yourself in the foot? Something. And we haven't really looked at it from that angle. That would be really useful, actually. Just example design patterns you can easily say in these languages that are bad. Yeah, good. Thank you. That's great. All right, in my very brief amount of time, which is negative, what would you guys like? One thing we could do is we could say, that was interesting. Let's take a break. And if you've had enough interesting for today, you can go. And then a few of us can stick around for another 20 minutes. Does that sound good?
Yeah, that's probably a reasonable idea. So,
OK.
people need to leave.
I will not be offended if you take off.
Stick around so we can see the rest of the talk.
We're mostly going to talk about language ideas at this point.
Okay. I guess you were going on a good track there.
OK. So if this was the part of the talk you had wanted to hear, I apologize.
It's all on videotape. We're going to keep capturing.
OK. Then you can suffer through it again, is what you're saying. Yeah. OK.
High speed.
There you go. That's good. OK. So the next thing I want to talk about is the foundation logic for Bloom, for our new language, which is called Dedalus, which if you're not catching the reference, you can talk to Peter afterwards, because he was an English major and I wasn't in college. So Dedalus is the foundation language for Bloom. As I said, it's the Datalog in time and space. Okay? And the first observation that sort of came out, and somebody right away, one of you guys pointed this out, was time has got to be really important. And in fact, space doesn't matter. So distributed systems aren't about space. They're about time. Basically, it doesn't matter whether the thing is like in the next room or 2 rooms over, or if the thing is in Albuquerque or it's in New York or if it's in Beijing. That only matters from a kind of performance perspective. Once it's far away and you can't clock with it, you can't do things atomically with it, it's distributed. Okay? So distributed systems are not about space. They're about whether you can atomically do stuff in time together. And that's the thing you should be reasoning about as a programmer, is about time. And so in Dedalus, there's 3 things you can say. You can say something is true now, something should be true instantaneously after now, or something's true asynchronously. Well, I don't like that word eventually, because yeah, people have a lot of connotations for that one. So I prefer later, or actually we just say async. Yeah. The other thing, so that was the first sort of conceit, was that Overlog was all about partitioning in space, and that was wrong. It should be about partitioning in time. The other conceit, I think, in the language, which is liberating, is that there's no database. Every fact is transient. Every fact is true only for one instantaneous time step.
Sounds like a streaming system.
It's very much a streaming system. Yeah, absolutely. But there's no windows, or there's no built-in windows. So every local node has atomic time steps. So on a given node, a fact is true for a single atomic time step, and that's it. All right? And I think you pointed this out before. Put a timestamp on every tuple if you like. Same effect. And it's a local clock time step, a local logical clock time step. And what's cute then is you say, so what is persistence? What is storage? It's just induction in time. Right? And what this is going to give us is a model-theoretic framework to talk about side effects and update, which is really quite cool. So all this stuff that we didn't get before about, like, what does it mean to do update? When do updates happen? That's all going to be logic now. And it's going to have a unique minimal model and all these lovely things we had for Datalog. So I'll show you this in just a sec. And then delay and failure are just non-determinism in assigning timestamps. So all the things we worry about in distributed systems will be asynchronous specifications with non-determinism in the timestamps. Right? And there's actually been work, there's nice work on capturing non-determinism in logics that we just lean on for this. Right, so we didn't have to invent anything. So here's sort of core Dedalus example. I know some event E, which has attributes A and B, and a timestamp attribute. Every table in Dedalus has a timestamp attribute, the last attribute. All right? If I know AB is in E at time t, then I know AB is in P at time s, and let's say t equals s. If you write a rule like that, that's a plain old Datalog rule. It's deductive. It says if I know EAB, I know PAB at the same time. That's plain old Datalog. If instead of t equals s, you say successor, this is next. This means instantaneously in the next timestamp, if I knew E at one timestamp, I know Q at the very next timestamp atomically, with no intervening state of Q. And then asynchrony just says, if I have a time t, then of all possible times in the universe, which again we will not store, all possible times in the universe, this is the logic expression from our Italian friends at UCLA for expressing non-determinism. Keyed on A, B, and T, choose an arbitrary S. All right, that's just the way to think about it. It's like for each A, B, T triple that satisfies these two rules, you pick an arbitrary S that is in the time relation. So this is just basically RAND, if you like.
Presumably that's S greater than T.
We actually like to say it doesn't have to be. And there are cases where it really doesn't. And this is all just logic, man.
So the arrow of time is time.
It turns out it has to do with how much non-monotonicity is in your program. So if you have a totally monotonic program and all it's doing is accumulating stuff, you can have it infer stuff that was true before, and it'll catch up. And then, Pete, what's the quote? The MIT quote?
Time is a device that was invented to keep everything from happening at once.
OK. But in most of our programs, because we do want to admit non-monotonic update, it makes sense if you do it in monotonic time, and it doesn't make sense if time has cycles. Yeah. So update gives you headaches if time doesn't go forward.
If you put a range limit on S, do you get the Cedar algebra out of this?
I don't know the answer to that because I don't know what you're talking
Well,
about.
Cedar algebra is 2 times, not 1.
I'm saying put a range on S. That gives you the 2 times. You say it has to happen within this period of time to be true.
See, but every tuple here only has 1 time. The tuple is not true for an interval.
No. The tuple has 1, but you could put an interval on top of that and say, we'll do the async random deferral during this period that tuple now applies.
You could probably say something like, this fact can only be true if it arrives within a certain amount of time.
Within an interval.
That's fine. Yeah, you could say that. Sure. So I don't know how that maps to your language. That would be hard work for me to. I'd first have to really understand what you're doing instead of vaguely understand what you're doing. All right, here's the sugared version, OK? So you don't really have to write that. That's horrible. If you want to write a Datalog rule, write a Datalog rule and leave out the timestamps. If you want to write a Datalog rule with next, say at next. And if you want to write later, say at later. Right, or at async. All right, so that's the sugared version of Datalog, Dedalus. Here's where it gets fun. Persistence. Persistence is induction. If P is positively true, AB, then P is positively true at the next time step, AB. So this is just infinite storage of that fact. All right? It's true now, and if it's true at x, it's true at x plus 1. Persistence through induction. You don't want to implement that. That's like RAM. All right, that's like implementing DRAM in your software, which is just a bad idea. You have to keep refreshing all your facts. But it's a fine model, and after all, this is just a model, right? The implementation is independent. Now let's suppose you want mutable state. All right, you want to do deletion. Let's have a convention. For every predicate P, which we'll call P positive for now, we will also have a predicate called P negative by convention. And if you like, this is like Ruby on Rails. You must name your tables the way I say so, because I invented it. But in fact, we can put sugar on top of this, so you always generate. You say P, and I say, oh, you mean there's a P pos and a P neg, and I do that under the covers. Now, hold on. Let me do this because it's fun. And then whatever you want to do, which is less fun. I'm sorry. You arrogant bastard. All right. If we know that A1B was in P pos at some time, and it was not also in P neg at the same time, then it is in P pos at the next time. It's a bug. What A? I don't see any A. Oh, this is on video. Go back in time. It's non-monotonic. All right. There's no A, man. But think about this for a sec. Let's look at this example. P12 is true at time step 101. Very nice. It's in P-pos. Okay. P13 is true at time step 102. Fine. P-neg has 1, 2 at 300. Is P-pos contain 1, 2 at 300? Yes. P-pos does not contain 1, 2 at 301. Because what we're saying is, if a fact is currently true and has been asked to be negated right now, it will be gone in the next time step. We break the induction.
Do you want to comment at the end of the first line?
I put a period.
No, first line.
No, that's just bad. That's bad, keynote wrap. This is the arguments of P-pos.
Oh, it is. It's the argument of 10. Okay.
Yeah. Sorry.
Like a separate statement.
Sorry.
Indented.
But the point is, right, the induction has been broken at time step n, and that appears because there's no induction to time step n plus 1. Right? This is actually extremely cool, because now what we've got is this is all just Datalog. There's no updates. There's no nothing. This is just good old-fashioned Datalog being used in a very stylized way, which means we have a beautiful, lovely model-theoretic treatment of state update and side effects. And all the tools we know about in Datalog can be thrown now at these programs. Jonathan.
You do have windows.
We have windows.
These are windows.
Yep.
They're little bitty windows.
You can create a rule that says for each fact that you add to P-pos, you add a P-negative with the timestamp being the original timestamp plus some constant.
You can absolutely implement windows. Yeah.
You could have also gotten rid of the prologue retract. You don't need it.
Which I wouldn't have wanted in the
No, that's the point. Is this works correctly in the logic framework without having to do it?
Yeah, actually, you know what would be, if I cared about such things, and what I care about seems to change over time, because I used to think programming languages were really boring. If I cared about teaching the Prolog community something, I guess we would go back and do cuts and all this kind of stuff and retracts.
Oh, with this?
With this,
yes.
Right? Basically, you implement.
It doesn't fit this model.
You do, but you have to implement the Prolog interpreter in Dedalus. Which is awesome. So we implemented a query optimizer in Overlog, which did bottom-up search. And then somebody on a review said, well, you say it's extensible. Can you do top-down search? And we did. In a bottom-up language, we'd implemented top-down search. So yeah, it's very doable. It'd be, like I say, if I cared, which I actually right now don't.
It also preserves all and and or parallelism that you have in pure Prolog. That getting rid of cut and getting rid of retract, that you can now do the logic, and this thing now parallelizes like crazy. Yeah, it's good.
Thank you. Okay, once we're in Datalog, now we can start writing theory papers and playing games. So we sent a paper off to Pods where we took all the two classical analyses you do to Datalog programs, and we recast them in this temporal model so that we could get their benefits. So one is stratification, which is finding out where your non-monotonicity boundaries are and organizing your program so that you step through them in a way that has a unique minimal model and that has a natural implementation. And we showed that you can do that with this temporal extension. And it does exactly what you just described. It tells you that there's a whole batch of stuff that, because it doesn't count, essentially, you can do it as parallel as you like. And so it points out in these programs, even with state update, it tells you where your races are at some level. And it tells you to wait for them. It tells you to hold out and wait till that race is done. And lock, somebody was talking about lock-free stuff. What's a lock? What's a semaphore? Counting semaphore, counting. Didn't I just say everything's about counting? Yes, it is. What this is going to tell you is where your locks should be. And if you want, they're counting. Sure. Yeah. It sounds really cosmic. I don't know if it's true, but it sounds good. And then also safety. When you have conservative checks that can tell you your program will terminate, we can translate those to checks over time. Okay, and that's useful sometimes. And the key is that time, and this gets to your point about going backwards in time. Time is a source of monotonicity, and we can use it in our analysis. If you know that time's going to march forward, you can say stuff about what your program is doing. You can actually take your program, you can unroll it into a plain Datalog program with lots and lots of these strata laid out one time step at a time, and then you can collapse the strata if you do something totally monotonic across two strata. So time is this source of monotonicity because facts from the past cannot negate themselves in the future. And therefore, many things that look, actually, the classic examples of non-monotonic reasoning from the database theory textbooks are fine in time. They look like flip-flop programs, and they're meaningful. They're well specified. They don't terminate, but they're well specified. You toggle between your beliefs. I win, I lose, I win, I lose. It's true, it's false, it's true, it's false. It's all fine. Right? It's all well specified. And so the static checks are easy. Wow. Yeah, OK, good. So a little more formalism. This is not yet written down, and we haven't figured out what to do with it. This is Pete's drawing of what Dedalus does. It takes these concentric circles are like strata in a single Datalog fixed point. So if you want, it's just a single Datalog fixed point. And then in Overlog, what we'd say is state update happens, and then you do another fixed point. In Dedalus, what we're saying is that these are next rules. All right, so these are the facts you know at the next time step, which define a selection on the database at that time step. Right? And then there's these asynchronous rules that go through the randomizer that pop in at some later time step. And there are these foreign agents sending us data from across the network. Because after all, we want to go back to doing distributed systems. We can't control when the messages arrive. And they could be written in other languages. They could be written in Java. So these arrive at some random amount of time, some random times. If everything you write is just nexts, and you don't have any laters, and you don't have any foreign things, your entire program's outcome is specified in the first time step by the base data and the rules. The only non-determinism, the only thing you don't know logically from the very beginning is these non-deterministic timestamp assignments. And, of course, the data and the timestamps of arriving stuff. That's what you want to describe in terms of the semantics of your program. All the semantics of the next stuff is here. It's given at the beginning. The rest of the semantics are captured in the timestamps on these messages. So we'll call that a trace. It's just an assignment of timestamps. And now, really what we want to talk about with program correctness is what are equivalence classes of traces with respect to certain properties. So like Church-Rosser property would say, can I prove that all traces, say, ignore the red stuff, but all assignments of delay give me the same answer? That's the Church-Rosser property. It says all traces are equivalent. Give me the same output database. But you could have weaker forms of equivalence. You could have equivalence classes on traces that are something else, that like, I don't know, the numbers in the bank accounts add up the same, even though the timestamps on the issuance of the checks are different. Right? And so I think we have a nice tool to talk about things like eventual consistency. I think you said something about eventually. Eventual consistency, loose consistency models and stuff in terms of trace equivalence. I think. We haven't done this, so this is pure conjecture. Maybe all we have is a pretty way of saying that we don't understand this stuff and nobody ever will. But I think we have a leg up. And then the other thing to keep in mind is if the red guys are also the Dedalus programs, kind of what we're capturing here is kind of things like Lamport clocks and causality and stuff, right? But we're capturing it in a way where we can dig deeper into the program and look at the data flow analysis of the logic. Right? So you can actually talk about causality with respect to the meaning of the program, not just like, oh, somebody sent me a message at a certain time and I couldn't possibly know what they were doing with that message, so I have to be very conservative. We can actually integrate the assignment of clocks with the semantics of the program. And so I think we can, I may be wrong, I may be underrepresenting what's possible in sort of classic TLA type stuff, but I think we have a lever here as well.
So TLA actually deals with things like, pure after and eventually, and
yes.
things over intervals, as does the Cedar algebra, which we mentioned before.
Okay.
You can say this is true from now to infinity. Every tuple has 2 times, not 1, to make that go.
A start and an end.
Well, yeah.
Okay.
Yeah. You get there from here with induction, but
yeah, it's not as pretty.
But you can do this with that by just saying T1, T1.
That's right. You can go either direction. You
So
can
you can
implement
go
one or the other.
way.
Yeah, good.
Either can simulate the other pretty efficiently, I would think.
But TLA doesn't include all of non-monotonic logic, right?
No,
to do that part.
I wasn't trying to get there.
And so that's where I think having these both in a single language, I'm hoping is going to help us reason better about stuff. And an example of that is like this notion of ACID 2.0. You say, well, if you have a set of interfaces and they're all associative, commutative, and idempotent, that's a good way to program distributed systems. Can we analyze these programs for those properties and then say, oh, we can relax? Trace equivalence will now be easy to prove because I've proved associativity of something. I think maybe we can, and we're starting to think about it. We're marching down that path. So best practices for building distributed systems have actually a logic constraint on what you can say in the logic. And I think maybe we can test for those constraints. All right, so much for Dedalus. It's really just a formalism, okay? So here's what I think of for Bloom, and then I'll leave you with this, because Bloom doesn't exist. Bloom is a fiction. It's going to be some version of Dedalus that's supposed to be great. But here's how I think about it, because it's fun. It's what I call the Bloom loop. So the Bloom loop is, it's an acrostic for Bloom. so it's easy to remember. So the Bloom programmer, what do? They're going to write a time step, essentially. They're going to say, given stuff that's come off the queue, what do I want to dequeue? So you can have some control over the asynchrony. You can postpone things. They've arrived, but I don't want to deal with them right now. So you can have basically a priority queue with a priority function. That'll define your trace. That gives you control over your trace. And then you'll write your logic, which is your now stuff. That's L. All right? And that's if you wanted safety testing in distributed systems, or it's assertions, it's invariants, it's derivations of new stuff. Then you write your operations, which are like state update side effects. That's really what next is. And then you need another O to make it spell Bloom. So that's the orthography step. Call that acronym enforcement. And then there's messages, which is later, and you'll send messages. So you show this to a programmer. You say, dequeue, test some stuff, make your updates in batch, send messages. This is not crazy. This does not look like European logic. This looks like an event loop programming design pattern. My ethnic roots are in Europe. I have a great respect for the continent. Shortest paths. Here's our shortest paths program. And I did a Ruby-style version of this for fun. So this is not Bloom. This is Bloom version -1. OK? And my guys aren't particularly fond of this, but it's better than not showing you anything. So here's batch for our shortest paths program. Every time a new path tuple arrives, or every 1 second, do the following. All right? Here's the logic. Here's the definition of the link table, key, value. Here's the path table, key, value, defined by link.each for each link, yield a key value pair for path. For each pair of path and link that match on to and from, yield the from to for the combined path. This is not great. This unification syntax is a little confusing, but so be it. All right, but these are comprehensions instead of for loops. They could be for loops. That'd be fine. And then shortest paths is kind of got a reduce in it, right? Because you have to do min. And again, this is pretty close to Ruby. It's a little bit of Python-y stuff in here, but it's kind of Ruby-esque. And then there's no ops in shortest paths because you never do any state update at all. And then there's messages to be sent. All right, but that's a kind of Bloom loop look at things. When we think about like our entire Hadoop file system implementation, this doesn't seem to help us much as a framework for thinking about how to factor that implementation into modules or functions or objects or what. So it's actually, it's cute, but it's not clear that it's all you need for structuring a program. OK. Now I'm actually going to be on time if you give me a 90-minute talk. So where are we going? Here's some stuff we're doing on the sort of system side, and then there's a slide of stuff we're doing on the languages side. And I realized as I did these two slides that there's no way we could do all this stuff with the size of the team we have. These guys haven't seen these slides, but they're going to kind of scare you. What we desperately need, which we're putting on the calendar, is to sit down and prioritize this list, add things to it, brainstorm some more, and then winnow it. But here's stuff that we've been talking about. Neil, who is an excellent and very experienced coder, is building a new runtime for Dedalus, or for Bloom, called C4, which is a plastic explosive. So it's part of the Boom project. And the target is to be able to do as many Paxos rounds per second as necessary from our Paxos spec. OK, so can we build Chubby for real? At this performance characteristics, the throughput we need. And to do that, you need very low latency message handling. And most sort of database engines are tuned for bandwidth. They're tuned for throughput. They're not tuned for low latency. So that's what C4 is, the challenge there. And it's coming along. Haryati came from Wisconsin, and he does storage and recovery. And we've been talking about this idea of failure as a service in the cloud. So the idea is if you want to do testing of your software and how it's robust to failure, you want to be able to do orchestrate large-scale experiments where you fail components in the system. And orchestrating that seems like something very natural in a high-level language. So we've been trying to put his ideas together for testing and software for storage together with our notion of declarative programming with this idea of failure as a service. And this is a very young idea, but it's exciting because Haryati's done a lot of really good work with declarative testing for correctness of storage systems. We've been talking a lot about Paxos and virtual synchrony and other group communication and consensus protocols, and I think we can make some progress here. I'm arrogant enough to think we can waltz into that area now with this new logic and make some progress. We'll see. We'll see. I don't know. And then we want to build some stuff. So we built Hadoop, and the next thing we built, which didn't use Overlog at all, was a streaming version of Hadoop called Hop. the Hadoop online prototype. It does continuous queries, and it does online aggregation, if you know what that is, without changing the MapReduce fault tolerance model. So it takes out the staging of maps and reduces, and it lets it stream while also doing the backup restart that's built into MapReduce. So that's kind of cute. Once you build that, you realize, my God, scheduling this thing is really complicated. And I'm sure you see this in Dryad. When you have a much more flexible programming framework, scheduling it on a parallel system is just, there's so many design variables. So we want to get back to our declarative scheduler to play with that space. So that's going to come back to us. And we want to build latency sensitive services because really this batch processing stuff didn't exercise performance and a bunch of other things. I've been working for some years now, as I said, on declarative machine learning, and we haven't lost that yet. I'm still collaborating with Carlos Gestrin on that. We've been talking about management and configuration, but actually doing nothing. Bill did a little bit of work on that, but he was just sort of a class project. And then I'm funded to do security stuff, so I hope I will. Here's the Bloom stuff. So where's Bloom going? We need to make the logic more approachable, and possibly a link-style thing with comprehensions is better. That's sort of like the Ruby I showed you than logic. But more importantly, like, as you think about building a lot of software, how do you structure code when this is your programming paradigm? And we've been working really hard to figure out, like, what's a function, or what's a call, or how does a programmer think about, like, a handler? It's all flat, and it's all intertwined. So we've been worrying about that. And then Neil was asking me, like, well, how does this relate to, like, stack ripping? I was like, I don't know, what's a stack? Like, what are you talking about? I'm really confused. So how does this relate to events versus threads? I don't know. I'm confused. So we want to understand this because this is how programmers structure their code. And so that's really important. I think I'm very optimistic that we'll be able to do neat static analysis stuff now that we've Dedalus in hand. So this notion of traces for testing for confluence, causality, and easy concurrency control. And then possibly taking the ACID 2.0 ideas and understanding them better. This distributed declarative invariance, I think, is a very big deal. So we're focusing on that. We've done some stuff with debugging because you get message provenance or just general provenance in logic fairly easily. So you can answer things like, why is this fact here? Or why did this update happen to this data structure? Or why did I get this message? I can tell you exactly. It was because this was true, and this was true, and this was true, and this was true. So that's kind of interesting. And there was work like this in our earlier project, but we haven't really exploited it enough. And then finally, if there's a theoretician in the room, this whole idea that they're long gone. Damn it. Damn it. So I'm working with Christos Papdimitriou on this. Basically, if resources are really free, if you believe the Yahoo guys, and I think they're nuts, frankly, but if you believe the Yahoo guys, as many machines as you want, no problem. MapReduce, we're going to win a benchmark, 10,000 machines. Could we have done it on 40? Yeah. But we did it on 10,000, because why not? It's MapReduce. It scales forever. If that's true, then the only thing expensive is coordination. Right? Anything you can do in the map phase is free. OK, well, how many coordination boundaries are there in quicksort? Or in sorting? To sort something, how many times should you coordinate? How many machines should coordinate each time? This is kind of an interesting notion of complexity. So what's the coordination surface? How deep is the coordination? How many times do you have to have a barrier? And for each barrier, how many nodes are involved? It's kind of an interesting complexity model. And then I think you can get randomized and approximation algorithms tucked into this model by saying, I'm going to step over a coordination boundary either speculatively and then just move on, which would be kind of approximation, or I'm going to step over this boundary and there'll be some cost to fix it if I'm broken, which is more like a randomized algorithm. So anyway, we're playing with this. I don't know. It's interesting. So some of the things we're thinking about, and now I'm 2 minutes over my really long talk, but there's references for the record.
I think that talk is 5 minutes.
It's fat. It's slow. Thank you for your patience.
So I would suggest we give the speaker a big round of applause. And